Welcome to this lab video. This lab video is on sputtering. Sputtering is one of the three techniques which we use, which we call as a physical vapor deposition technique. In sputtering, what we do is we introduce argon gas and there is a creation of plasma. Again, depending on what kind of sputtering you are using, DC sputtering, RF sputtering, DC magnetron, RF magnetron, and this plasma, right, these argon ions will hit the source material, dislodge the atoms and will deposit onto the substrate. Let us see how it is done in real time. Alright, so we will see the sputtering tool, how the vacuum is brought in sputtering tool, where is the source loaded, where is the target loaded, that is our substrate is there, where is the source is there, how we are creating a plasma, how we are adding the argon gas, and so on and so forth. So, look at the video. If you have again any question, please feel free to ask it using our NPTEL forum.
Welcome to the lab demo. Today we'll focus on sputtering and we'll see how this tool works and how we can deposit our desired material using sputtering. Now, as professor might have told you, the different fabrications steps involved in fabrication. Three major steps are additive, subtractive and patterning. In additive step, what we are doing, we are adding some material onto our substrate or a wafer. That material can be a metal or a oxide or a active layer. Depending upon which material we'll be depositing, we'll go with the tool required. Now, in physical vapor deposition, we are physically either melting the material or we are bombarding some gases and the dislodged target atoms are coming and depositing onto the substrate. In this process, we require the chamber or where we are depositing our material should be under vacuum. Vacuum is required because we want to increase the mean free path between two atoms, as in when the material is melting and the vapors are going up and condensing on the substrate, we want it to follow a molecular regime wherein one particle is not able to see another particle, and without any collision it is directly going and sitting or condensing onto the substrate. In physical vapor deposition, we have three basic tools in physical vapor deposition. First is thermal, second is E-beam, and third is sputtering. So disadvantage in the thermal and E-beam is that first the material, where the source material where we are keeping it, the melting point of that material should be higher than the source material. Metals like tungstens have very high melting points, and if we try to deposit using E-beam or thermal, it will not reach its melting point with the resistive heating. For that, and for the dielectrics or the oxide whose melting points are really high, we'll require some other technique which is called sputtering, wherein what happens is we have the target which is the source material. We are bombarding argon atoms to this target. So we have a very high electric field near the vicinity of the target, and whenever these argon atoms are coming inside the vicinity of this electric field, these argon atoms are getting ionized, and my target is at a negative potential. So this positive argon atoms will come and hit my target. Once it hits the target, it will dislodge or it will knock out the target atoms from the base material or target material, and this knocked out atoms, neutral atoms, will come and will get settled down or deposit onto the substrate. So this is the basic theory for the sputtering, and now we'll see how to operate this tool. For this, I'll press start or IO. Every time I press start, I'll press reset. This will reset my, this is a hardware reset. It will reset my all the electronics, and we can start the tool once all the safety interlocks and water cooling will be checked at the point when I press reset. I log in using my credentials. This is the main menu. Now there are options to choose from. First, I'll go to most desired tabs to look for is the system control and the source control. In these two, I'll go to my system control, and now you can see a display wherein I can monitor all the pressures or the pressure inside the chamber. This this is the roughing pressure, and this is the backing pressure. The backing pressure will come into picture when the chamber pressure will go 10 raised to power minus 3 millibar, because the penning gauge, which it gives me the reading of the backing pressure, will come into picture, or it will start showing the reading after 10 raised to power minus 4 millibar. Now to start the tool, I have two options, either to start or vent. I need to start the tool. What does this start will do is it will start my turbomolecular pump. Turbomolecular pumps works on very high RPM speed, and it requires at least 5 to 10 minutes of time to come into its full speed. To save that time, or to give that time to the turbo, I'll press start. This start doesn't mean that I have started evacuating my chamber. It is just a start for my turbo pump to start accelerating, and you can see the prompt that turbo pump is accelerating. This will take 5 to 10 minutes of time. Meanwhile, I'll show you other display of the tool. This is the emergency stop button. If there is an emergency, if you can see a smoke coming out from the tool, then you should press this EMO button. This panel is the temperature control, wherein if you want to increase the substrate temperature, then you can set the temperature and decrease or increase the temperature using this buttons. And once you enable from the display panel, the substrate will start heating, and it will reach to the set value which is displayed here in green, and what is displayed here in red is the actual value or the actual temperature of the chamber. This is the digital thickness monitor. Here we'll see what is the rate of deposition and how much thicker film has been deposited to a point, to a particular point. This complete panel is for RF sputtering, and this panel is for DC sputtering. This tool can accommodate or can be used for RF sputtering and DC sputtering. So difference between RF and DC sputtering is, suppose we are hitting argon atom to a target which are ionized. The argon atoms are ionized. Now this argon atoms to go into neutral state, it will need one electron so that it will come to a neutral state and it will go out of the system. When we are depositing any metal, metal has lot of electrons, plenty of electrons, so easily argon atom will get one electrons from the metal which we are depositing, and it will go out of the system. But in case of oxide or dielectric, wherein the free conducting electrons are very less in oxide or dielectric, the argon atom will not find that electron to neutralize, which can be compensated with the RF signal. So RF signal is a pure sinusoidal signal. In first half of the cycle, the plasma will strike, and in second half cycle, the negative charges or the signal, the negative charge will be provided by the RF signal, and the argon ion will neutralize and will go out of the system. Now you can see on the prompt that turbo is ready, and that means that turbo has reached to its maximum speed, and now we can vent the chamber. We'll vent the chamber because we need to place our sample for the deposition. Currently the chamber is in some vacuum, so I'll press vent and I'll wait for a couple of minutes to chamber to vent. The chamber has vented, and it is safe to open the chamber. Before we open the chamber, I just give a brief of what the chamber. This is the viewport, wherein if you want to see whether the plasma has striked, or to see how much deposition, or to see how the substrate is rotating or not, this is a viewport from where we can see. This is the motor control for the substrate holder to rotate. Now I'll open the chamber. So here there are two magnetrons. The left side magnetron is dedicatedly for the RF sputtering, and for the right side magnetron is dedicated for the DC sputtering. In today's deposition, we'll be depositing tungsten using DC sputtering. So we have placed our target here, and we have covered this RS sputtering with the aluminium foil so as to eliminate any contamination while the tungsten is getting deposited. This is the substrate holder, and I can remove it. So this is the substrate holder, and we can place our substrate onto it. As you can see, this magnetron is at some angle, so the ideal position to keep the wafer or the sample is at the center of the chuck. Now these are the halogen lamps for substrate heating. Using radiation heating, it will heat the substrate. This is the spindle to rotate, to place the substrate holder, and it will rotate as and when required. And the last one you can see is the QCM. It's a quartz crystal monitor, where it has a quartz crystal which has its own resonant frequency. Once some mass is getting deposited onto the quartz crystal, its frequency will change. That change in frequency will be calculated in how much amount of deposition has happened. Now it's time to load our sample. We'll load the sample on the substrate holder, and we'll keep it back on the spindle and keep the chamber for cycling. So this is a glass slide on which we'll be depositing the tungsten, and as you can see, it is a transparent slide, and I have cleaned it using IP acetone and DI water, and I have given a nitrogen blow to it so as to dry the slide. Now it's time to load this slide, and these are the clamps I'll be using to hold my sample. These it is the safest option to hold this sample, and why we are doing this is because we'll be placing this substrate holder upside down, so we want to make sure that our samples stay intact, and it should not fall while we are placing the samples in the chamber. Now we have tightened the screws, and we will check whether our slide is moving or not. It is not moving, so we are okay to take this substrate holder to the vacuum chamber. Chamber is already in the vent condition. I'll open the chamber and I'll place this substrate holder. Now the chamber is in atmospheric condition. I want I want a connection between my pumps, which is already running, and chamber. To do that, I'll press cycle. So now, if you can hear, that rotary pump has started, which will take down the chamber pressure to 10 to the power minus 3 millibar. Once that is done, turbo pump will will come into action, and further pressure will be reduced from 10 to the power minus 3 to 10 to the power minus 6, or the desired vacuum pressure required for the deposition. To get a closer look, or to get into details of the pumps and the valves, I'll just go to the system view, and here it is a mimic diagram of the whole system. This is the chamber, and these two things are the magnetron, and there are two lines going. One going through the turbo pump, and one is directly connected to the rotary pump. When I press start, what happens is that turbomolecular pump start accelerating and reaches to its maximum speed, and there is a vacuum generation, or the line evacuation of this line. Once I press cycle, that the chamber from atmospheric pressure, or the air inside the chamber, will be sucked out through this line using rotary pump first. Once the chamber pressure reaches 10 to the power minus 3 millibar, the high vacuum valve will open, and the evacuation will happen through this line. Right now, the chamber pressure has not reached to 10 to the power minus 3, so you can see this valve is closed. This valve is open, and these two valves are open. This line is already in evacuated condition, and through this valve, my chamber is getting evacuated. Now we'll go back to system control, and we'll wait for 1.5 hours for our vacuum to reach, and we'll come back once the desired vacuum has reached, and we'll resume our deposition process. So after waiting for 1.5 hours, we have reached to the desired vacuum level. That is now, as you can see, it is 3.2 e raised to power minus 6 millibar. So this is our desired vacuum level. Now we can start our deposition. To go into deposition mode, there are three options now available with me: either seal, process, or vent. To go into deposition mode, I'll go into process mode. So once I have pressed the process, what has happened is the backing valve, which was sucking out the air from the vacuum chamber, now it is partially closed. Why? Because for this deposition, we will be using argon gas. That argon gas will come, will get excited and will move out. So there should be some gap in the wall through which this argon gas will go out of the chamber. That's why the system has gone into throttle pumping mode. Now here I'll go to the source control. In the today's deposition will be DC sputtering. So I'll enable my DC supply. Once the DC supply is switched on, all the display will be highlighted here. This is the voltage where this knob is for voltage. I'll increase my voltage to 600 volts. This is my current knob. This is my power knob. Here I have already set my power to 300 watts. And this is my current knob. When I want to start the deposition, I will start increasing the current. This is the argon flow. I'll I'll open the valve for the argon flow. Now I'll increase the voltage to 600 volts. First, I should set this toggle button to the set mode, and I will set my voltage to 600 volts. Once my set voltage is 600, I'll move the toggle button to read mode. After this, I'll give the argon supply as 5 SCM. At the same time, I'll monitor the sputtering pressure because this plays a major role while deposition. Now I'll increase my flow to 8 SCM. And one thing I'll want you all to notice now, the read power is 0. Once the plasma strikes, this power will change and you will see some value here. That means plasma has strike. Now it is 8, argon flow is 8, and the sputtering pressure is 3.7 E minus 3 millibar. Now again I'll increase to 10. Once I did this, I'll set my current to 0.5 amperes. As I'm increasing my current, there are chances that plasma will strike with the 10 SCM gas flow. But it might happen that the argon atoms inside the chamber is not sufficient and the plasma is not getting strike. So once I go to 0.5 milliamperes, I'll increase the gas flow as well. Now it's 0.45 and I'll increase my argon gas flow to 12. Now as you can see, my current is 0.5 amperes and my argon flow is 12. So maybe the argon atoms near to the target is not sufficient. So what I'll do, I'll just open and close the shutter. Now as you can see, suddenly from 0 to 148, 150 the power has increased. That means plasma has striked. Now we'll have a closer look at the viewport, and if the plasma is there, you will able to see a glow discharge when I open this viewport. So as you can see, a bluish, light bluish color plasma is strike. That means the argon atoms are getting ionized and it is getting bombarded onto the target. You can see there is a shutter kind of thing which is stopping the deposition to happen on our desired substrate. Once I'll open this shutter and the deposition will start happening on the substrate. Now we'll switch on the DTM as well and I'll press stop. Okay, now as you can see, my read voltage has decreased to 500. That means my current is not sufficient as well as my argon flow is also not sufficient. So what I'll do, I'll increase my argon flow to 15 and I'll increase my current to 0.55 amperes. Now it's time to open the shutter so that the deposition will start happening onto the substrate. Also, we need to rotate the substrate holder so as to get the uniform deposition. So here I have enabled the rotary drive and I am setting the RPM to 10 RPM. And once again I'll go back to the source control and I'll open the shutter. And here I'll press start. So whatever the change is happening in the DTM, on the right hand side is the thickness which is getting deposited. On the left hand side is the deposition rate. So right now it is getting deposited 27 or 28.4 Armstrong per second and the deposition till now is 670 nanometers and it is going on. To increase more power, we can increase the argon flow if required, but I feel this is the sufficient power for the deposition to happen. I will deposit for around 4 to 5 minutes, depending upon how much thickness I want. Here the deposition rate is really high, so my desired thickness has been reached, and to stop the deposition, first I'll close my shutter, I'll decrease my argon flow to 10, I'll decrease my current slowly to 0. You can see now the power is decreasing. That means we are not supplying sufficient power for the argon atoms to get ionized. Once this is 0, I'll decrease my argon flow to 5. All the way back to 0. And I'll close the gas valve as well. Now I'll move this toggle to set voltage and I'll decrease my voltage all the way back to 0. Meanwhile, I will stop the rotation Once my read voltage is below 50, I can switch off the DC supply also and the DTM as well. Now I'll go back to the system control. Now either I have option to seal or vent. Ideal practice is I'll first cycle it for a few minutes and then I'll vent the chamber. So to do that, I'll press first seal. So the walls has come back to its normal position, and then I'll press cycle. What cycle will do, whatever the argon was present inside the chamber, all the argon will come out, and we'll keep for cycling for a few minutes and then we'll vent. It has been 4 to 5 minutes we have put for cycling. Now it's time to vent the chamber and see how the deposition has come up. For that, first I'll press seal. What seal will do is it will isolate the chambers from the pumps, and then I'll press vent. Now you will hear a hissing sound. That means atmospheric air is coming inside the chamber and bringing the chamber pressure to atmospheric pressure. I'll try to open the chamber now. Still there is some more vacuum left in the chamber. We'll wait for a couple of seconds more. As you can see, the glass slide which we have kept at the time of the vacuuming is nicely covered with the tungsten. And first, initially the glass slide was transparent, and now it is shining and nicely coated with tungsten. Now I'll remove this glass slide and put back the chamber into vacuuming. Why? Because ideally this chamber should be always in vacuum condition. So as the chamber is now in the atmospheric pressure, I need to put back into cycling. So again I'll press the cycle. Before that, I have to again isolate my pumps and the chamber. For that, I'll press seal and I'll keep my chamber for cycling. Sufficient vacuum has reached so that we can stop the tool. Now we'll stop the tool, and that's all for today's lab session. Thank you.